Hello and welcome to Webinar Wednesdays from the Deep Carbon Observatory. My name is Katie Pratt and I'm part of DCO's engagement team based at the University of Rhode Island. This webinar is brought to you by the engagement team and DCO's Synthesis Group 2019. It's my pleasure to introduce Anirudh Prabhu, a data scientist at Rensselaer Polytechnic Institute, where he works with DCO's data science team, which is led by Peter Fox, Kathy Fontaine, and Karen Rogers. He's currently pursuing his PhD, and his research interests include data modeling, machine learning, and data visualization. Today, Anirudh is going to talk to us about analytic methods for big data sets. This methodology is increasingly important in the geosciences in order to make sense of big data resources such as EarthChem, NavDat, MinDat.org, and Paleobiology Database. This webinar will use real-world geoscience use cases to help you solve scientific problems by applying quantitative algorithms and accurately interpreting the results. Now, for a bit of housekeeping before we get started, the presentation portion of the webinar should last about 25 minutes, followed by 15 minutes or so to answer any questions you may have. If you have questions during the webinar, please use the chat function at the bottom of the screen to type your questions. At the end of the presentation, Anirudh will answer the questions in the chat first before we move to an open Q&A. If you have your webcam turned on, please turn it off at this time. You can turn it back on during Q&A. So with that, I'm pleased to sign off and hand it over to Anirudh.
Thanks for the introduction, Katie. Hello, everyone. As Katie mentioned, my name is Anirudh Prabhu. And today we're rounding up the Data Science for Geoscience summer webinar series with a talk on analytics. So the data analytics pipeline usually involves the following steps. You start by processing the raw data. Fang covered the data processing webinar a couple of weeks ago, or a month ago, I would say. We then use descriptive analytics to explore the data, gain basic information about the data, and then we try to understand the information stored in the data by identifying patterns, relationships, and trends that may be hidden in the data. We can also use predictive analytics to explore potential future scenarios, and then use prescriptive analytics to recommend a course of actions based on all the possible future scenarios. So in this webinar, we'll start with a basic introduction, explore descriptive models, identification of patterns and relationships, and end with predictive analytics. So the most common question I get asked when I'm giving a talk on analytics is what the difference between analysis and analytics is. So analysis focuses on transforming and modeling the data for discovering useful information, while data analytics is a methodology. In analytics, we use the results and insights we gain from the analyses, for example, from descriptive or predictive models, and use them to recommend a course of action or as a guide for scientific decision-making. Application of these methods is as much art as it is science, so we have to consider a balance of the methodologies that we apply. So let's start off by loading our data sets. We use the read.csv function for reading in our data from a file. The first table contains uranium mineral data. As you can see, we have chemical formula information, we have age, locality, latitude, longitude, structural complexity, unit cell parameters, and many more features. Since the previous part of the data of the webinar focused on the data processing and cleaning aspect, I have directly also loaded a cleaned version of a data set here. The second table contains a uranium locality data set. Here we basically have the age information, the locality name, and all the minerals contained at a particular locality. So now that our data set is loaded and ready, we go to the next step, which is the descriptive analytics aspect of it. We begin first by exploring the data. So descriptive or exploratory analysis helps us to understand the features in the data and how they are distributed and what features may be of importance. John Tukey's quote interestingly describes this process. It says, exploratory data analysis is an attitude, a state of flexibility, a willingness to look for those things that we believe are not there, as well as those things we believe are there. So the first thing we need to do is look at a summary of the data set that has been loaded. So this can get a little overwhelming. As you can see, we have a large number of features in our data set. When we summarize our entire data set, we look at the structural complexity features, which are V and IG. We have unit cell parameters, which are A, B, and C. We have age information, color information, and locality information. So simple visualizations like a histogram help us, and even a box plot can help us see the distribution of various parameters and can help us understand the importance of these features. So if you can look at the histogram, which I'll go back to, you can see the distribution of the maximum age of uranium minerals. So what we can see here is most uranium minerals are young, except for a small peak that occurs between 1500 to 2000 million years. You can also see the distribution of values of the various unit cell parameters. And you can see that the C parameter has a much wider distribution. The next step is identifying patterns and relationships. So once we have a general understanding, we try to explore what hidden trends might be in the data set that we're exploring. The two approaches we're going to explore here is a clustering approach and an association rules mining approach. Both of these are kind of unsupervised approaches since there's no outputs available for this data. There's a wide variety of algorithms that can be used for each of these tasks. Unsupervised learning, as I mentioned earlier, does not have any output information. The task is to spontaneously find patterns that may exist based on the features that exist in the data. So clustering is a task where we need to find similar or dissimilar objects that exist in the data based on the distribution patterns and relationships that exist in this data. So the algorithm we're going to use is called the PAM, or partitioning around medoids algorithm, to perform the clustering. The first step of this algorithm is to use a distance matrix to calculate how similar or dissimilar these elements are. We then use this distance matrix to run clustering simulations and find the optimum number of clusters. To find the optimum number of clusters, we use silhouette width, which is a measure of how distinct each cluster is. The rule of thumb is any combination with a silhouette width of 0.35 or greater is considered well clustered. But as most things in the real world, it's not as easy or common to see such a high silhouette width. What we see in this simulation is the optimum number of clusters is 2 for our data set with a silhouette width of approximately 0.17. So for the next step, we go ahead and actually run the clustering algorithm with a value of k is equal to 2. The result we see is a fairly well-clustered group with a little bit of overlap. While this is the result of the clustering algorithm, in the analytics methodology, we explore these groups to find out which features are most important. And we look at the geological parameters that exist in each of these groups and see what we can leverage from the data that exists. The next step we're going to look at is an example of the association rule mining, or market basket analysis as it's popularly known. This algorithm is used to discover relationships that can exist between various attributes in the data. These relationships are then encoded as rules, which another system can use for potential decision making. For association rule mining, we use the second data set that we loaded, which contains the locality information and the age information and the minerals contained in the locality. So what we look at is the name of the locality that you see here and a list of minerals that exist in that locality. And we have this for every locality in the world which has uranium minerals. The next step is to process this data set to use the association rule mining algorithm. Since Fong covered data processing in a lot of detail in the last webinar, I'll just skip through this step, but I'll show you what the processed data set looks like. So what you can see is we've converted the raw data into a matrix-like format with zeros and ones. So what you see as rows is the locality ID, and for every locality, if a particular mineral is absent, it's a 0. If a particular mineral is present in the locality, it's a 1. So you can see here. It's a very sparse matrix, but this is ideal for our analysis. The next step is to actually mine for the association rules. Here we use the a priori algorithm, one of the oldest and most popular algorithms for association rule mining. The results we see are actual rules that are generated based on the associations that were found in the data set. If you look at rule 3, for example, it says that if a locality has turbinite, uranophane alpha, and autunite, then uraninite should be found there. Each rule created has 3 metrics: support, confidence, and lift. The higher the lift, the more interesting or novel the rule is. There are also visualizations that help us summarize these rules. So the first summarization that you can see is what's called a grouped matrix. In this grouped matrix, we see that it's able to summarize the left-hand side of the rules with the right-hand side of the rules, and the larger the circle, the more times the rules occur. So you would know that these rules, these combinations occur more, and they are very important in the data. Another example of a visualization is a parallel coordinate plot, which shows us a summarization of how these rules occur and in what order they should be read in. And probably the most important summarization is a graph or a network of the 100 rules that are created. The first 100 rules that are created. So you can see when minerals co-occur with each other in the rules, they're connected in the graph. The size of the circle or the node that you see is corresponding to the support, and the color is corresponding to the lift, which I mentioned earlier was a metric of how interesting or novel a particular rule is. Now that we've found some patterns and trends, it's time to move on to possibly the most popular step in the analytics pipeline, which is the predictive analytics metric. So predictive analysis uses statistics, machine learning, data mining, and other AI techniques to make assertions about the future. The 2 main methods for predictive analytics are the classification method and the regression method, both of which are supervised learning algorithms. Supervised learning methods use a trained model. The trained model will contain output information. So we are able to assert that for a particular new input, what should be the ideal output. So on to classification. Classification models are usually used when the predicted values are categorical, ordinal, or discrete. Here we assign a new data point or observation with a known set of classes. As an example for classification, we can see I'm creating a model to predict the redox state of uranium minerals, and I'm giving it a whole list of parameters, which are the dependent variables. So what you can see when the model is run, first of all, I run a conditional inference tree model for this. So the output is a tree format where it tells us what the most important parameters are to predict redox state. As you can see in the diagram, there's color, paragenetic mode, topology, and luster for uranium mineral. So these parameters help us predict what the redox state of a uranium mineral is. So now we can use the actual trained model to run predictions. We use the predict function in R to do this. What you can see is we have a 93.82% accuracy for the model. This is a very great result. But a simple look into the data will tell you that the redox state of the minerals are highly biased towards the redox state 6. So the model can get a high accuracy by predicting 6 most of the times and not predicting any of the other values. So we have to be very careful of model results like this because we have biased data. There are many techniques to overcome this model bias and avoid overfitting, but we can get into that in a more detailed webinar. So now that we've covered clustering and a classification problem, it would probably be a good time to talk about this. Many people are confused about what the difference between clustering and classification is. This slide shows us the difference. The left side of the slide is focused on the clustering, where initially there are no known classes, and we come away with classes, known classes based on the similarities and the features that you see on the data. while the right side focuses on the classification problem, where we have predefined classes that exist in our training data, and we predict the outputs for new data that exists. So I like to use the coin analogy when I'm explaining this difference. Let's say you have a bunch of coins given to you and you're told to group them. You can group them in many ways. You can group them based on size, shape, weight, color, year of minting, or the more obvious coin value. This is basically the clustering approach when you're told to group them, but not how to group them. On the other hand, if you're given a bunch of coins and you're told to group them simply based on the monetary value of the coin, that would be a classification task. Because not only are you told to group them, but you're told exactly how to group them in a supervised manner. Lastly, we would cover the regression problem. Regression is most commonly used when the predicted variables are numeric or continuous. Here we use the conditional inference tree model again, which can run regression and classification problems. And the task of our model here is to predict the maximum age of a uranium mineral. So once I load a clean data set and run the model, you see that the most important features in predicting the maximum age of a uranium mineral is the hardness of the mineral, the topology, and the paragenetic mode. So once we know this, we can use this model to again predict the maximum age of the mineral. To validate a predicted mineral in a regression model, there's multiple ways to do this. The simplest way to do it is to look at the residuals, which is the difference between the truth value and the predicted value for a particular data set. What you can see here is this model does not perform very well. We see that there's a large distribution in the values when the value should be very focused on like near the zero value. But this happens very commonly in real world data, that you don't get an ideal model results. There's multiple ways to optimize this. You can pick and choose your parameters based on a PCA algorithm or a factor analysis that tells you what are the important features, and then you can further optimize that by looking at other techniques and cleaning your data a little further. Well, I'm about done with all the topics I wanted to cover for this webinar, but as far as the topics for the data analytics pipeline goes, we are nowhere near done yet. There's prescriptive analytics, visual analytics, mixed models, and many other advanced topics that should be covered, but maybe we'll cover that at a later date. To end, all the slides in this talk, along with the code, were all created in a Jupyter Notebook. You can also access some of these Jupyter Notebooks or create your own at the DCO Jupyter Hub, which is at jupyter.deepcarbon.net/hub/login. And thank you so much for listening to my webinar, and thanks for attending.
Thank you, Anirudh. That was just great. I loved when you mentioned that analytics is as much an art form as a science. And I think that you are not only a wonderful scientist, but an artist as well. So thank you. It was really great. And with that, I'd open it up to the audience. Are there any questions out there? If not, I have one. Under patterns and trends, you talked about the rule metrics. And to me, that looked like you had an unlimited way to analyze your data. And I was wondering if you could just give us some insights as to how you define those rules.
Absolutely. So since I've also finished a little early, I have plenty of time to go into that. Let me just go back to the slide. So yeah, so going back here. So the a priori algorithm, like I mentioned, runs association rules. And for every rule created, hold on a second, I'm not able to get to the exact slide. So there's three metrics, like I mentioned. There's a support metric, a confidence metric, and the lift metric, which I mentioned was the metric for interestingness of the rule, right? So the support metric is fairly simple. It gives you an assertion. It tells you how many times a particular combination occurs in your data set. So if you look at the first rule, it tells me that these four minerals occur in the data set certain number of times, and support is the ratio of that. So if it occurs one time only, it'll be 1 upon the total number of transactions that you have. So that's the first metric, which is a fairly simple one. The second metric is called the confidence metric, which is the expected number of times that a combination of minerals should occur in your data set. So it's a simple probabilistic join of 2 minerals or n minerals occurring together in the data set. So and then the lift is a very simple ratio of the confidence to the support. So in simple words, if I have to explain this, if I say 4 minerals occur in the data set 5 times, but they are expected to occur in the data set 50 times according to the algorithm, that means we can infer that there's about 45 more times that it should occur in the real world. And so we can make the assertions that you should go look for these combinations of minerals. So if you find a locality in the world that has the first 3 minerals, then there's a high probability of you finding the 4th mineral there. So that's how we create these association rules, and that's kind of the message, that's the inference or the insight that we look for from this model.
That's great. Thank you.
Yeah.
You made it very clear. And Hiroko from Ohio State has a question too, and hopefully.
Hello, do you hear me?
Yes.
Yeah.
Oh, okay, great. Hi, nice meeting you. I'm Hiroko from the Ohio State. I'm a 4th year PhD student.
Yes.
And currently working on a clustering analysis. And my question is that so my problem setting is that I use like multiple variables and I try to see the similarity between the variables and try to make a cluster. And my question is, how do I able to validate that how much variables that I have in my cluster analysis setting is to be accurate enough to create the cluster?
Right. So
does that make sense?
Yeah, that makes sense. So it's a very common question. It's a good question to pose. So first thing is you would want to start with all the variables to see what every feature that is assigned to your data set would give. There are the obvious ways where you would know the importance of a certain variable in your data set by running a PCA, principal component analysis, or factor analysis, depending on the type of the variable. So if the variable is numeric or continuous, you would want to run PCA. If you want to look at if you have categorical variables, you would run a factor analysis because they are discrete, unique factors, right? What really helps in this case is when you finish your clustering, you can plot the clustering results in what is called a PCA plot. In R, you have multiple packages that do this. There's ggfortify, which gives you a ggplot version of a cluster plot, where once you plot your clustered results in a 2-dimensional space, so you project it into a 2-dimensional space, you can also plot the eigenvectors for every variable that you have in your data. So the length of the eigenvector and the direction of the eigenvector tells you how important that variable is to the clustering process. So if you notice that a certain variable is not very important to your clustering process, you can remove it based on the data and then retry your clustering for more accurate, better results. Also, as I mentioned earlier, there are metrics like the silhouette width metric that I showed for telling us how distinct these clusters are. So ideally, you want a high silhouette width because you want distinct clusters, right? The cluster should have similar objects, but every other cluster should have objects that are very dissimilar from each other. So in the ideal world, you would have a very high silhouette width metric as well. So these are ways you can validate and improve your clustering results.
Okay.
Thank you.
Thank you.
Anything else from the audience before we wrap it up? Well, I'd like again to thank you, Anirudh. That was really enlightening. And also, this wraps up the data science series for this summer. And I would encourage all of you online to tell your colleagues how valuable this series is. And it's available on Deep Carbon Observatory's YouTube channel. And go have a look. But we have, because the webinar series have been really successful, we are continuing them in the fall. I just wanted everyone to mark their calendars. On September 19th, Adrienne Forfrost from the University of North Carolina, Chapel Hill, will be presenting her MetaSeek program, which is a program for researching and retrieving metadata. And that will be at 2 p.m. Eastern. And October 10th at 4 p.m. Eastern, because the presenter, Sabin Zerovic, is in Australia at the University of Sydney. He's getting up at 7 o'clock in the morning to present for all of us. And he's looking at how DCO researchers can apply modeling techniques in a program called EarthBytes, which integrates tectonic plate data into this really cool visualization. With that said, thanks again. Hope to see you in the fall when we bring you more practical ways to improve your science. Take care, all.